Hey friends, welcome to the Adventures of Blink. I am of course Blink and I am so glad you've joined me today. Make sure you like, subscribe, and click that notification bell so that we'll stay connected. And of course you can drop by the blog at any time for more content as well. Now last week we built a couple of classes to describe our paddle and our ball, and we integrated them with the game window. But while they move, they don't interact. Today we're going to focus on a core concept in video games: collision detection. We've actually done collision detection kind of already. Remember in the ball class when we made it check for the edges of the window? That's the concept we're shooting for. Detecting the edges of the screen is a little different from having objects collide though. It's very simple by comparison. The cool part about this is that our Pygame library handles most of the heavy lifting for us. For starters, we'll look at how the ball will collide with the paddle. Okay, so before we get started, I want to make sure we build our new branch and keep things organized in our code base. So you'll notice that I'm on main if you look in the bottom left. And so what we're going to do is git checkout -b episode 5. And now we're on the episode 5 branch. All of our changes today will be posted there. That'll make it easy for you to dig through the code later. If you want to go back and see sort of the progression of how we built, each branch is going to stay in the repository separate. Anyway, now that we've done that, we're actually looking at the game window, because in order to collide with things, you need access to both of those things. So we're going to make the paddle and the ball collide. And the only place currently where both of those items show up in the same code is in the game window. And that makes it the logical place to put this. Now, to be fair, if we were going to expand the project to have deeply object-oriented structure, we would probably end up with another place that's not the game window itself. The window is supposed to be just about displaying things on the screen. And we're sort of co-opting it to do some other things here. But the size of the project, the fact that it's not a huge project, doesn't lend itself to that level of granularity. So we're here in the game window, and you can see we have the code from doing the update on the ball so that it moves around the screen. After that update occurs, we need to do a check. So what we're going to add is a collision detection. If ball.rect.collide.rect. Okay, so think about what we're saying there. There is a rectangle object within the ball class, and we're asking if it collides with self.paddle.rect. Okay, so if the ball and the paddle collide, then we're going to have to make some decisions on what happens next. First of all, we're going to go ahead and log this occurrence. So we'll do a log debug, and we'll say paddle hit. And we're going to do the paddle was at this location, so we're going to grab the center X of the paddle rectangle. And then we're going to add in the ball rectangle. And then the other thing we should do, because at some point it may vary, I don't think we're going to do that in this season, but we would theoretically have the ability to track the ball speed, and so it would be an important thing to write in the debug there. All right, so that's all it takes to decide whether the ball and the paddle have collided. What we're doing within this if block is taking action based on the assumption that it's happened. So now we know that the two have collided. What are we going to do different? Well, we're going to first set up a variable to capture the new velocity. And the way we're going to do this is off of a function that we actually haven't written yet, but I'm going to go on ahead and name it here. and then we'll build it. Okay, and we're going to pass in the rectangle for the paddle and the ball rectangle and the ball speed, just as we looked at previously, right? So, oops, I think I got overzealous with my, there we go. Okay, so you might be asking yourself why we have to calculate this angle in a separate function. And the reason is because if we just played by natural physics rules, there would be nothing in the game that was actually fun. All you would do is keep the paddle moving, and whenever the ball bounced off of it, it would just continue on its natural path based on the physics of the situation, and nobody would ever be able to do anything to change it. It's just you're basically staying alive. And that's not really fun. What we want to do is give the player a chance to control it, to sort of aim their shot, if you will. So the way we're going to do this is based on where the ball hits the paddle, like what part of the paddle it hits. So if it hits on the left side, it should bounce, like that's considered aiming to that side. And so if the ball comes in, regardless of what angle it comes in at, when it hits, if the length of distance from the center, if you will, right, is on the left side of the paddle, or I keep forgetting I'm doing this on camera, right? If it's on the right side of the paddle as you're looking at it, then I want the ball to bounce off hard to the right if it's like on the edge. And if it's just kind of a little bit right of center, then it should bounce kind of up to the right. And the same thing for the left. So if you hit directly in the center, that's going to bounce straight up. But if you hit on either side, it's going to choose an angle of attack based on how far over you were. So if you use the edge of your paddle, it's going to go wildly off to the side. But if you use the center of your paddle, it's going to go straight up. That's the way we want to think about it. That's the calculation we'll do in there. We're going to skip out on that for just a moment and finish up what happens at this level of the collision detection, and then we'll go build that function in just a second. All right, so the next thing we're going to do, actually we should probably log the velocity that came back from this. So vnew. We're going to do self.logger.debug, and we're going to say new velocity. And we're going to pass in vnew there. Okay. And so that way we know what came back from the bounce angle thing. We can watch that in the debug log. Now we're going to update the ball velocity. So we're going to do ball.velocityx equals vnew. And vnew is actually going to be a tuple. So we're going to grab the first element out of it. And then we're going to do ball.velocity and we're going to do vnew 1. All right. And then the last thing we're going to do, because anytime that you have a collision detection like this, there's the chance that because of the velocities of the shapes and like the distances that they would have moved, it might be overlapping. And so the ball may actually be like under the paddle in a little bit, like a few pixels off, which would foul up all of our calculations for the collision detection on the next iteration. So we want to make sure we leave ourselves in a healthy place. And what we're going to do is set the bottom of the ball rectangle equal to the top of the paddle. So now it has a velocity that's taking it away from the paddle, and it's also at the same space, which means the next frame is not going to collide with the paddle anymore accidentally. So we'll do ball.rect.bottom equals self.paddle.rect.top. All right. And that will take care of the entire collision detection process. Now, the only thing we haven't done, so entire was probably not an operative word there. but we're going to have to think about this velocity thing a little bit harder. All right, so what I'm going to do is come up here to the top of this because I want the method. Actually, I'm in a class, so it doesn't technically matter, but I just like having the helper things up above. It makes them easy for me to remember. Like, I know that run is going to be at the bottom of my class window. Okay, so let's go see if we can figure out how to calculate the angle. We're going to do calculate bounce angle, and we're bringing in the ball and the paddle and the speed. And then we're also going to have a max angle, because we don't necessarily want this to be like, if we were to do the math directly off of the center point, then we would be saying that 0 degrees is straight up, so that's center, and then every degree beyond that is a part of a 90 degree in one direction or the other. But we don't want to go a full 90 degrees, because if you hit the ball directly sideways, the game goes on infinitely because it never comes back down. So we don't want to end up in that boat. What we want to do is push the ball upward. It will always have some degree. And so I'm picking, I think, probably like 70 as a default there, just to say that the angle will never be more than 70 degrees off the center. So we'll do max angle degree equals 70. And because we're going to be doing this, we're going to be doing some trigonometry on this, we're actually going to make sure to use floats here. Otherwise, you end up with really boring results because the angle never calculates well. Okay, so that's our function signature. Let's start building this thing. All right, so the first thing we want to do is grab a couple of variables, local variables to work with. So we're going to do a float of the paddle dot center x. Okay, and then we're going to do the relative hit location. So relative to the center, how far out did it hit? And so to calculate this, we're going to need the ball center x done as a float. And you'll notice I'm casting all of these things as floats, even though center x is going to be an integer. We want to make sure that we're casting them as floats so that the math comes back with some approximation in it, and then we can adjust. All right, so then we're going to subtract the paddle center. And that way we know how far away they were from each other. And then we're going to do a division problem on this, right? We're going to divide by float paddle dot width divided by 2. All right, so let's go over the math here. What we're doing is figuring out the relative to the center position, where did the ball hit? So we're taking the ball's center position and the paddle's center position, and we just have 2 points that we're comparing. So the center x of the ball minus the paddle center tells us how many pixels apart they were. Okay, and then we're going to do a division by the width of the paddle divided by 2, because we want to know what percentage of the paddle, like how far away from the center in terms of percent are you. So you've got like 100% of the way you hit on the very last pixel of the paddle. 0% of the way you hit directly on top of the center point. And that's what we want to use as the calculation. All right. Now the next thing we're going to do is clamp the value to ensure it stays within the range of -1 and +1. So that way, if there are edge overlaps, we don't create hassles for ourselves. So we're going to update the relative hit to be -1. Okay, 1 relative hit. So this is a quick way in Python. You have a max and a min, and if you wanted to make sure that something falls between them, then -1 is the low end and +1 is the high end, and so you're going to do the min of the high end and the relative, like the number that you're looking at. Whichever one of those is smaller, you're going to pick. Generally speaking, we're hoping it's relative hit. And then you're going to do the max of that with -1 so that you end up always within the range. All right. The next thing is to check the absolute value. Because we don't actually want to calculate literally every angle possibility. We want to set these to sort of have some boundaries. So if you were within 0.25 of hitting in the center, you're going to treat it as if it was the center. And that gives you like a sweet spot on the paddle. It says anything within 0.25 forward or backward is going to be a sweet spot hit. So then you could do equals 0. Now the other thing you want to check for is on the very ends. So if the absolute value of the relative hit is less than 0.5, then you're going to do some math. Relative hit equals a random. It's not necessarily math, is it? We're sort of going to give it a little bit of a random value. And we're going to go between 0.01 and 0.1. So if you hit the center of the paddle, you're going up. If you hit the next little ring of space out there, now you're in wobbly territory. And so we want to add a little bit of randomness to the way that the ball bounces. That's going to make us adjust as a player to something happening that we can't necessarily control. Then we're going to do if the absolute value of relative hit, got to type a little bit more before I autocomplete, is less than 0.75, then we're going to do relative hit equals random dot uniform, and this is going to be a different set of random numbers. So we're going to go from 0.1 to 0.25. So if you hit within the middle spot, you get a little bit of random because you're still close to the sweet spot, so you can kind of control it. But if you hit further out, you're going to get a wider variety of angles back. All right, so after we've done this relative hit thing and sort of scoped it into 3 sections, max angle, and I'm going to do this as radians. So math.radians so that sets the maximum number of radians that we can actually use. And then we're going to do bounce angle equals relative hit times the max angle radians. All right, now just because I didn't do it right now, I did it earlier in the season. I wanted to remind you that math has to be imported. So up here, I have an import for math. And that's why we did that, because I knew I was coming to this point later on in the situation. Now, we have a bounce angle created, but that doesn't help us necessarily with velocities yet. Because a bounce angle just tells us which direction the ball is going to go. Now remember, we held on to the speed. The speed becomes important here because the next thing we're going to do is a new velocity x and a new velocity y. So I'm going to do both of these without anything after them just to get started. Now, how would you go about calculating this? This is where your trigonometry comes in. So the next thing you have to do is negative speed times math.sine of the bounce angle. And then you're going to do negative speed times math.cosine of the bounce angle. Oops, mistyped that. All right, so let's have a little trigonometry refresher here to see how this works. We have a paddle in our game, and we have a ball, okay? And when the ball hits the paddle, it's going to bounce off at an angle. Now we're basing all of our angle decisions off of the center line vertical that's 0 degrees. So we know it's going to be some number of degrees over here. And I'm going to go ahead and extend this so we have a triangle developing. I'm sure you can see where I'm going with this, right? Now, the default speed of a ball is 10. We set that in our ball class. So we know that the ball is going to go at the speed of 10 that direction. What we don't know is what is its vertical velocity and its horizontal velocity. Those are the pieces we have to figure out. So in order to tell, and this is going to be an x and a y, right? So in order to tell what those are, we can use our trigonometric functions, okay? Sine and cosine. So the sine of our angle, and I'm just going to call the angle A, right? The sine of A equals x over 10, because sine is opposite over hypotenuse. So we go opposite over hypotenuse, okay? And then the vertical component is going to be a cosine. Cosine of A equals adjacent over hypotenuse. So cosine of A equals the adjacent over the hypotenuse. Okay, now we've divided up the vector here of 10 into its vertical and horizontal components. And those are the speed things that we have to send back to our ball class. Remember, we're holding a velocity x and a velocity y variable within the ball class. That's how it works. All right, so now that we have our new velocity x and y components, what we have to do is pass them back, because this method is now finished. It's calculated what we need, and it knows that we're going to do a tuple. So I'm going to put parentheses, and we're going to do new velocity x, new velocity y. Okay, and that's what comes back from our calculate bounce angle. So if we come back down here to where we were doing our collision detection, if we detect the collision, we calculate the bounce angle based on where we collided with the ball and paddle, and we log the new velocity so that we'll be able to see that in the debug statement. And we've now passed the new values back to the ball. So the ball knows what its new velocity vectors are. After doing that, we made sure to shift it just a little bit in case it happens to be overlapping. And we're done with the collision detection. So we should be able to test this out. So we're going to do Python source main.py, and let's go see what happens. And look at that ball. Except we have a bug because we bounced right off the screen. All right, so we're going to go back to the ball class and see what we messed up. Well, as I scan down through the code real quick, I see one obvious thing, like that jumps right off the page at me. And that is, up here, I used bounds x and I called a function. Here, I did not add the parentheses. And I'm betting that that caused Python to behave differently. And that's why we didn't get what we were supposed to get. So let's go try to rerun this now. And let's see what happens. There goes our ball. And look, it's now bouncing. And whew, that's actually kind of fast. But if you notice, every time we bounce, we're hitting the paddle in a different place. Ooh, that was a close one. And see, we're able to adjust based on the way that the ball bounces off the paddle. Like, we get the ability then to control. Oh, there we go. That was a good bounce. We hit right in that sweet spot. And now our game works. Now we can bounce the ball around the screen. We're making good progress toward a breakout game. We'll wrap up here for this week. Okay, so let's see if we can go on ahead and push this code up. We're going to do a git status just to see where we are. And we have two files that changed today. We changed the collision detection in the game window, and then we fixed our bug in the ball. Now, I'm going to go on ahead and do something here. I usually don't do this, but it's worth seeing that you can control how commits get pushed into Git. We covered a little bit of this back in season 3, but I think it's worth just a refresher. So I can do a git add source core ball.py, and then I can do a git commit, but instead of the -a, I'm just going to do the -m. And here I'm going to put bug fix for wall collision detection. Okay, now look, when I do git status, I've only pushed up the changes to the ball. So now I'm going to do git commit -am because I want all the files, all one of them that's left here in staging, and I'm going to do collision detection between ball and paddle. Okay, and now I'm going to push that up. So that if we go over here to GitHub, we will see that episode 5 has arrived. Let's go on ahead and create our pull request, because that's going to merge it into main. And now we're good to go. We can come back to our front page and we can see that main has episode 5 in it, and episode 5 is still a separate branch. All right, that wraps up today's adventure. Remember to like, subscribe, and click the notification bell. And of course, stop by the blog. I'll see you next time.